So we read this first project in class on Wednesday about inventory decisions, keeping costs as small as possible. It's a very common kind of business application. You could say it's part of inventory management. We are trying to manage, in this case, how much computer paper we keep on hand, how often do we order, and how much do we store, ultimately to keep costs as small as possible. Now, there are other considerations as well. You want to think about profit. How much does the computer paper contribute to your profit and that kind of thing? But certainly cost is part of the game. And what do we want to do? We want to review, first of all, the problem summary. We've got the computer services firm that uses many cartons of computer paper every week. We saw from the data that it was about 150 cartons of paper per week. They want to know how often they should order computer paper from an out-of-town discount supplier to keep their average weekly cost as small as possible. Very, very practical kind of problem. But there were competing arguments. One argument is to place large orders infrequently, not very often, because there's a $360 charge for every order, regardless of the size of the order. If the company orders too often, like every day, you're going to be paying that $360 charge every single day. That doesn't sound like a good idea. So that's an argument for placing large orders, maybe, I don't know, once every 3 months or something like that. On the other hand, if you do place large orders every 3 months, then you're keeping your paper in the store, in the warehouse for a long time, and that's costly. There's opportunity costs. You could use that money for some other kind of investment, for example. And there's also holding costs. That storage takes up part of your warehouse. That costs money because you have to rent the warehouse. Placing larger orders infrequently will result in a lot of money being used up at one time, like it says here. This holding cost will make the average weekly cost too high. Oh, that's a typo there. That should be TOO instead of TWO if option one is pursued. So we should probably place small orders more frequently. In reality, what we're going to see is the best answer is going to be some sort of middle ground. But what exactly is that middle ground? We want to use calculus to find out. Yeah, we can anticipate the final decision. In the end, it's probably a middle ground, but we want to figure out how often should we order the cartons and how many cartons should we order with each order. The following costs are figured out by the managers. You are like a consultant going in and learning about their operations and learning about their costs, and they're turning to you for the modeling, the math, to help them figure out what to do. There is, again, the purchase cost of $22.46 for each carton ordered per week. There is the $360 delivery carton for each order. And then there's the holding cost, which you wouldn't know what the holding cost would be. You have to rely on those managers to tell you, and they estimate that it's about 18 cents per carton per week. $0.18 per carton per week, okay? But again, you've got a lot of cartons, maybe hundreds of cartons, so that can add up. We've got three main variables to think about. N is the number of cartons per order. T is the weeks between orders, okay? You could call that weeks per order if you wanted to. Like if you order once every 5 weeks, then it's 5 weeks per order, or maybe even 1/5 of an order per week, even though you can't do literally 1/5 of an order per week. In class Wednesday, I called the average inventory between orders I, but here in this PowerPoint presentation, I'm calling it I bar. It is an average, and in statistics, putting a bar above a variable is a common way of emphasizing that it is an average, and that's what I'm doing here. We are making some assumptions. In doing mathematical modeling, whether it's in science or business, you have to make some simplifying assumptions, because if you don't, the math just gets too hard. So it's always a balance between, well, keeping it complicated enough that it's still somewhat accurate, but keeping it simple enough that you can actually do something with it. Somewhere in between is an ideal middle ground to shoot for, but you are always assessing how good your model is based on feedback. You know, you get an answer, you ask questions about how good this answer might be, how reasonable it might seem. If your answer is unreasonable, you should not consider it. I once gave a calculus problem in a test that involved related rates, which we're going to talk about later today. And it involved the speed of some boat, and a student happily on an exam solved for the speed of the boat, and it was faster than the speed of light. Okay, not a reasonable speed for the boat. They should have said something to the effect of, I know this is wrong, but I can't figure out where the problem is. I would have given them an extra point. Okay. We need to think about how reasonable our answers are. We need reality checks. So again, we've got an assumption of an average usage of 100 cartons per week based on company records. And you may recall on Wednesday, we assumed that these cartons were used at a uniform rate. We're going to see a graph illustrating how the inventory goes down over time along a straight line. We're going to order paper so that it is timed to arrive just as our supply runs out, just in time delivery. Of course, in real life, you really wouldn't want to do that exactly, right? Just as you're using the last carton, oh, now the delivery arrives. That doesn't sound like such a great plan, but it does keep things simpler for modeling purposes. It makes the math simpler, so we assume it to keep the math simpler. And then once we get our answers for the math, we keep in mind that, oh yeah, we really don't want true just-in-time ordering. Maybe close, but not exactly. N and T, the number of cartons per order and the time between orders, we're going to assume vary continuously so that we don't have to think about discrete math. We can think about using the techniques of calculus. In the end, of course, since n, for example, is an integer, a number of cartons, we do need to round our answers to get practical answers in the end. Okay, here's maybe one where you want to start taking notes. I did write down the initial equation last time. That these costs, the total cost is the purchase cost plus the delivery cost plus the holding cost. Think about units. That's really key to helping you solve problems like this. This cost is ultimately in dollars per week. That's the thing we're trying to minimize, is the average weekly cost in dollars per week. So whatever quantities that you are combining here, the key to thinking about how to combine them is to think about those units. Every carton costs $22.46. You could think about the units for that cost as $22.46 per carton. How do you convert that cost to dollars per week? Multiply by a quantity whose units are cartons per week. Yes, you order n cartons per t weeks. The cartons here will cancel, giving you a quantity when you multiply of 22.46 times n over t dollars per week. That's the purchase cost. Now, again, keep in mind that it's possible that you order every 10 weeks or something, that t is 10. And so calling this a charge in dollars per week is really a long-term average. It's not something you are actually paying every week. Then you got to the delivery cost, $360 per order. You want to convert that to dollars per week, so you need to multiply by a quantity that's in orders per week. T has units of weeks per order, so its reciprocal has units of orders per week, 1 over t. And then we've got the holding cost, $0.18 per week per carton that is stored. You could convert that to a unit that has a fractional unit like this, dollars per week times cartons. Don't worry about trying to imagine what that means. You don't need to worry sometimes about units like that and imagining what it means. Just realize that if you then multiply by a certain number of cartons, the average number of cartons per week, the cartons do cancel here and you are left with dollars per week. The orders canceled here. So all these things do give you something that is in now dollars per week. And when you simplify it, you get the final formula right here. Now, that could be thought of as a function. You could look at that expression and say to yourself, you know, I don't know what n, t, and I bar are. I can think of those as variables. You could think of this thing as a function of 3 variables, n, t, and I bar. But if we're going to use calculus 1 techniques, that's a problem. We're not doing multivariable calculus. We're doing calculus 1. single variable calculus, we want to take ordinary derivatives, not what are called partial derivatives, at least today. So what do? This is our objective function that we want to minimize. What are the constraints that will allow us to get rid of two of the variables and just focus on one variable? There are constraints. We can figure out what those are. This is our function. I'm abusing notation here. I could have called this function another name like f, but I'm using the same letter C here to represent both the dependent variable and the function name. That is technically bad notation, but people do it all the time. Just realize it's bad, but people do it all the time. So we will play along and do it here anyway. I really should use a different letter there. Yes, like I just mentioned, it would be nice to eliminate two of these variables to the total costs will just be a function of one of them. If so, then we could use techniques of single variable calculus. Okay, the next slide is got the details of how to eliminate, well, one of the variables at least. Where are these constraints going to come from? Well, one of them comes from the fact that we're going to assume we use 150 cartons every week. That, remember looking at the data last time, that was a basically constant usage rate. That is one fact that is going to be one constraint that relates N and T. N and T can't vary independently of each other. They are related. They are constrained. If you know one, you know the other. At least if you assume just-in-time delivery. Let's eliminate N. Recall that we assumed that the average carton usage was 150 cartons per week. That's not the same as the average storage of cartons. That really would be, if you think about it, like 75 cartons per week, if we ordered once per week at least. That's the same as the ratio of N over T. Why? Think about it. Just try examples in your mind. So like if we ordered once every 2 weeks, if T was 2, and we're using 150 cartons per week, N would have to be 300. We'd have to order 300 cartons every 2 weeks if we're using 150 cartons every week, right? 300 over 2 is 150. If we order once every 3 weeks, T is 3. N would have to be 450. 450 divided by 3 is 150. If T were 4, N would have to be 600. This ratio is always going to be 150. And if you solve for N by multiplying both sides by T, you can say that N is 150 times T. That's a constraint that we can now substitute into the function to rewrite the function as a function of just T and I bar. No N's anymore. So remember what was here before. What was here before was N divided by T. That got replaced by 150. And I think there was no other N in the equation. So that's really the only substitution that we actually need to make. 22.46 times 150 is 3,369. And so now the function has been simplified a little bit to a function of 2 variables. That's progress. Function of 2 variables is simpler than a function of 3 variables. For the function of 3 variables, if you're going to imagine it completely, you'd have to imagine either a 3-dimensional hypersurface in 4-dimensional space for its graph, or level surfaces in 3-dimensional space along which the function is constant. We will talk about that a little bit next Monday. We'll visualize some of these higher dimensional things. But now we're down to a function of 2 variables. Its graph would be a surface, a 2-dimensional surface inside 3-dimensional space. Or if you're looking at the level curves in a 2-dimensional plane, you can look at those curves where this function is constant. That's relatively easy to visualize, but it still requires technology typically to help you draw it because it's typically too hard of a problem to draw by hand. Anyway, it's progress. We want to make more progress. We want to get rid of, say, I bar. How do you do that? Because we assumed an average use of 150 carts per week and just-in-time delivery and continuous variables, we can graph the inventory level as a function of time like this. And I'm actually making one more assumption here without stating it. I'm making the assumption that the usage rate in cartons every day is effectively constant. Okay. So T, for example, if T were 1 month, effectively 4 weeks here, we'd be using 100 N cartons in 4 weeks, that would be 600 cartons. This graph would be going from 600 down to 0 as T goes from 0 to 4. It'd be going down at a constant rate of 150 cartons per week. Its slope would be negative 150. It's a linear rate of usage, not just over the whole week, but even every individual day or every individual hour, if you will. The fact that we have this jump discontinuity at time T and time 2T and time 3T to go up to level N again is the modeling of the just-in-time delivery. If we did not have just-in-time delivery, we would still have a jump discontinuity, but the graph would keep going higher and higher, and our inventory level would keep getting higher and higher until it was too full for the warehouse. And that would not be good. So this keeps things simpler. Based on this, what is the average inventory level? I hope it's pretty clear that I bar is N over 2. Right? If you order once every four weeks, 600 cartons, then 300 would be your average inventory level. And that is what they said is the part of the cost of the storage that should go toward our formula. I bar is N over 2. So in the formula, I can now replace I bar with N over 2. By the way, if these graphs were not straight lines, if they were curves, then I bar would be more complicated. But once we learn about integration, we would actually have the tools to still figure out I bar, even if these were curves instead of straight lines. Maybe we'll even do that in a couple weeks. Therefore, I bar is N over 2, and N is 150 times T. Therefore, I bar is 75 times T. Again, if T were 4 weeks, N would be 600. N over 2 would be 300. 75 times 4 is also 300. You get the same thing. So now we've got everything just in terms of T. It's in terms of one variable. We can use calculus 1, single variable calculus, to help us optimize this. Before we do so, before we look at the details of the calculus, try to imagine what the graph of this would look like. T is our horizontal axis. C is our vertical axis. I hope it's pretty clear in looking at this formula that there's going to be a vertical asymptote at T equals 0. It's certainly undefined when T is 0. T equals 0 effectively means you're ordering every instant. No, that doesn't sound like such a good idea. $360 charges every instant of every day, and it's not practical for another thing. That would be very costly. Your cost goes up to infinity as T goes to 0. So this cost is coming down. But then when T is large, this cost is close to 0. When T is large, I don't know, like if you're ordering once every, let's see, T is weekly. If you're ordering once every 20 years, that's 20 years in weeks, over 1,000 weeks, this fraction would be less than 1, not contributing much to the cost. But this quantity would be large. If T was over 1,000, this would be over 13,000. That's the dominant term when T is large. The graph acts like that function when T is large, like a linear function with a slope of 13.5 when T is large. It's not a perfect graph because it's hard to do with PowerPoint. Somewhere there's a low point, it seems. There's got to be. By the way, the graph doesn't ever go below 3369. That would be a quantity maybe about there. So it would be 3369. 3369. Hard to write with a PowerPoint pen here. Your minimum value is not going to be below that. Okay, now let's look at the calculus. Here's where the details get kind of nasty because it's calculus, but you've got the ability to understand it. And you got it all here at once. So the derivative dc dt is right here. Is that right? Well, the first term was 3369. Its derivative is 0. The second term was 360 times t to the negative 1. its derivative is negative 360 t to the negative 2. And the third term is 13.5 times t, a linear function. Its derivative is 13.5. There, yeah, that's the derivative. What are we after? We're after a critical point. Set this derivative equal to 0. Solve for t. Negative 360 t to the negative 2 can be written as negative 360 over t squared. You could bring that to the other side of the equation. Divide both sides by 13.5, and then take a square root. T is about 5.164 weeks per order, about 5 weeks in 1 day. That's what the math is telling us, how often to place our orders. Think about what that would mean about n. It would mean n would be that number times 150, and that would be over 750. 760, 770, 780, something like that would be the number of cartons that should be in every order. Is it really a minimum? We saw graphically that it seems reasonable that it should be if you want extra confirmation. The second derivative is always positive for all t positive, so the graph's concave up. We are focused on positive t's, not negative t's, right? Negative t's don't make any sense. Graph's concave up for all t, and so it's really not even a local min, it's a global min at this quantity, and the total minimum cost per week on average is going to be $3,508. Again, that cost is not going to happen every week because the deliveries are just once every 5 weeks. So the $360 charge per delivery and the $22.46 per carton, that's going to be an infrequent cost. The holding cost is more consistent, like every day. Effectively, though that doesn't mean you pay your rent every day, but you've got labor costs and that kind of thing. So this is a long-term average. It's not literally a cost coming off your books every single day or every single week even. So in your budgeting, you got to think about it long-term, like over the course of at least 1 year. If it's almost every 5.2 weeks, and there are 52 weeks in a year. So you almost think of this as a cost that you got to pay like about 10 times a year, since there's 52 weeks in a year, and this is close to 5.2 weeks per order. Okay. And yes, about 775 cartons per order. Next Monday, we're going to continue thinking about this, but we're going to generalize it. We are going to think about the 3 variables altogether, n, t, and I bar, and imagine functions of 2 and 3 variables and graph them. And we are also going to introduce parameters for those costs, the 2246, the 360, and the 0.18. What if those numbers are wrong, or if they change? We want to know how sensitive our answer is to changes in those quantities. The formulas are going to get very complicated looking because there's going to be a bunch of letters all over the place. But if you keep your wits about you and do the calculus in the same kind of way, you can still solve it. And you get a very powerful thing. You get infinitely many solutions to infinitely many problems. Wow. They're all related problems. They're all related to this. And they give you the flexibility to handle changes in market conditions. That's very, very powerful. That's a very, very powerful use of calculus outside of science and engineering.